For decades, mobile connectivity relied on networks acting as transparent conduits, moving data from point A to point B. 6G marks a total structural departure. The industry is rebuilding the infrastructure into a self-learning organism, where artificial intelligence and environmental sensing are natively embedded into the physical layer. This shift has moved beyond the theoretical. As of 2025 and 2026, research has transitioned into intense hardware prototyping, preparing for a projected $300 billion annual market by the next decade. The standardization path is governed by the 3GPP. Following Release 19, the industry is finalizing foundational requirements for 6G. Release 21 represents a critical shift. Scheduled for 2027, it delivers the first technical specifications for mass commercial rollout. Unlike previous generations that relied on hybrid deployments, 6G is designed as a standalone system. This architecture prioritizes immediate monetization in vertical sectors, specifically industrial automation and autonomous transport, over general consumer broadband. To orchestrate these complex industrial environments, engineers must first solve severe physics failures at the microscopic level. 6G targets data rates exceeding 1 terabyte per second. To achieve this capacity, the network must exploit the massive untapped bandwidth in the Terahertz spectrum, spanning frequencies between 100 GHz and 10 terahertz. The physics at these frequencies are unforgiving. Signals experience extreme path loss and molecular absorption, resulting in a 40 decibel output power deficit that traditional radio hardware cannot overcome in outdoor environments. This comparison shows why traditional silicon reaches its limits in the terahertz range. Survival requires transitioning to advanced 3V materials. Indium phosphide is the sole material capable of driving power amplifiers beyond 200 GHz, with a roadmap meeting the 1 terahertz spectrum. At milliwavelengths, the distance between radio components and the antenna must be minimized. 6G utilizes antenna-on-chip configurations, fabricating the antenna directly onto the amplifier substrate. Packing these clusters generates intense heat, necessitating synthetic diamond or graphene heat spreaders to prevent degradation. Terahertz communication requires reinventing semiconductor physics before software can begin to route a single bit of data. Once the physical signal is established, the network must interpret it. In 6G, artificial intelligence is an architectural primitive, natively integrated into the physical layer, governing decision-making across the entire topology. Neural networks are replacing traditional static signal processing chains. This allows hardware to process raw, in-phase, and quadrature samples directly, enabling base stations to identify received waveforms without high-level signaling. The accuracy of these AI detectors is essential for reliability. Current neural models achieve near-perfect accuracy in identifying subcarrier spacing and waveform types, which is required to prevent synchronization failures in multi-numerology deployments. This precision enables waveform agility. The system utilizes standard OFDM for stationary users and instantly switches to OTFS for high-mobility scenarios, like high-speed rail, to maintain spectral efficiency. This intelligence is managed by an AI orchestrator, championed by the AI Win initiative. It replaces single-purpose hardware with a software-defined stack that coordinates communication, sensing, and computation layers. If the orchestrator identifies radar interference, it executes spectrum agility, freezing only the affected frequencies while keeping the rest of the band operational. This AI operates as an autonomic nervous system, instantly adapting raw radio frequencies to survive crowded or obstructed environments. The high capacity of terahertz waves comes with a trade-off. They are easily blocked by urban structures and foliage. Maintaining a connection in these environments requires the network to actively alter its physical surroundings. Reconfigurable intelligent surfaces allow the network to use urban structures as active components of the link. These surfaces use thousands of switchable elements to bend or focus signals around obstructions, ensuring connectivity even without a direct line of sight. This spatial awareness is driven by integrated sensing and communication. By utilizing ultra-wide bandwidths, 6G base stations double as high-resolution radar sensors. The resolution requirements for this sensing are highly specific. The system can achieve 1-meter accuracy for drone tracking and sub-centimeter precision for hand gesture control, all without requiring active electronics on the target. Sensing-assisted communication uses this perception to predict channel blockages before they happen. If the system detects a physical obstruction moving toward the path, it proactively switches the link to a better line of sight. This data feeds real-time digital twins. In a smart factory, the network synchronizes physical robotic movements with virtual replicas at centimeter-level precision. Through the convergence of sensing and communication, the network acts as an active participant that perceives and interacts with the physical world. 6G extends high-speed connectivity to oceans, mountains, and the stratosphere, creating a multi-layered 3D architecture. This non-terrestrial network architecture involves 3 layers: low Earth orbit constellations for primary broadband, high-altitude platforms in the stratosphere for disaster recovery, and geostationary satellites for global backhaul. Using direct-to-cell technology, standard 6G handsets connect directly to satellites. The system dynamically reassigns applications between terrestrial and space-based links to maintain a continuous connection without specialized hardware. To power this massive global sensing and communication grid, 6G mandates aggressive sustainability architectures to prevent a spike in energy consumption. AI-powered sleep modes shut down entire sections of the radio access network during low-traffic periods, reducing total energy consumption by up to 30%. For IoT endpoints, 6G utilizes ambient backscatter communication. These devices operate by reflecting existing radio signals to transmit data, enabling a battery-free global sensor grid. 6G achieves global ubiquity by forcing the network to intelligently scavenge and conserve its own energy. Holographic telepresence serves as the stress test for the 6G stack. It requires the extreme bandwidth of terahertz frequencies for volumetric video and the sub-millisecond latency of AI-native routing to keep interactions real-time. 6G routes these 3D holograms directly through the standard mobile voice infrastructure. This network-native pipeline allows users to receive holographic calls in their native dialer without third-party apps. For more complex simulations, a VR pipeline utilizes over-the-top rendering at the network edge. Offloading the heavy computational processing to the infrastructure allows XR headsets to remain lightweight and low power. The race to standardize these pipelines is a primary driver of geopolitical competition. Securing standard essential patents dictates which nations will collect royalties for the entire global 6G ecosystem. China leads in 6G patent volume, accounting for over 40% of global applications, reflecting a national priority for dominance in sensing and terahertz transceivers. The United States maintains a strong position in software-defined stacks and spectrum management, ensuring a bifurcated struggle for supremacy over the next decade's standards. This competition ensures that 6G is equally a technological achievement and a geopolitical battleground, defining national security for the 2030s. An AI-native network capable of high-resolution mapping across the globe presents new risks that traditional security models cannot address. 6G systems utilize zero-trust architectures and physical layer security. This uses the unique, fluctuating characteristics of the wireless channel itself as a cryptographic key, preventing interception at the radio level. These systems are being built to transition to quantum-safe cryptography, ensuring that the critical infrastructure remains resilient against future computational threats. This vertical stack represents a total departure from traditional telecommunications. It integrates indium phosphide hardware to overcome terahertz physics, orchestrated by native agentic AI at the cognitive core. It uses sensing-assisted communication and reconfigurable surfaces to interact with and map the physical world in real time. As the 2030 commercial rollout approaches, 6G represents the transition to an intelligent environment that perceives and adapts to the physical world around us.